Hi, welcome. I'm Lucian, and today I'm going to talk about reverse engineering of error-correcting codes. It's so nice to be in Berlin. I did not yet visit this awesome tower or awesome needle-shaped object. But anyways, I hope throughout this presentation you'll realize what is the relationship between a needle-shaped object and memory corruption. So yeah, let's go on with the presentation. Do you remember Rowhammer? So Rowhammer, anyone? I cannot say, okay, I guess many people raise their hands. So Rowhammer is still kind of new, I would say. First, it was documented in 2014. So what it gives us, there is like a memory reliability problem, which gives a primitive that flips one bit somewhere or several bits somewhere. So maybe it's hard to control. However, in 2015, like 1 year later, someone already showed several exploits. So basically, these were privilege escalation exploits. There was a kernel exploit that was using the Rowhammer to change some bits in the page table entry, thus mapping some resources that were used by the kernel. So then you can also do like a sandbox escape. So this was already known in 2015. Yeah, so about mitigations, there aren't that many yet. However, everything is work in progress because we still want to thoroughly understand how Rowhammer is working. So we are making progress, but in order to propose a decent solution, we really have to understand the phenomenon. So my work is actually in the direction of mitigations, but it's more offensive because I'm going to show why one of the defenses doesn't actually work. So let's do a refresher on how Rowhammer is working. So let's assume we have, this is like a view of memory. Memory cells are organized in rows and in columns. With the code snippet on the right, we can trigger the bit flips. So the code snippet is just a tight loop that accesses two rows. Which are apart one row. So they do have another row which is not really accessed now. And if you do this fast enough for several times, the row in the middle could expose a bit flip. So while you don't have access to this row, you manage to cause somehow a bit flip in that row. So in another part of memory, you manage to have a write one bit or more primitive. So this is how Rowhammer is working. We can take two properties which are interesting for us today. So the Rowhammer can cause some bit flips, not like an infinite number of bit flips, not any bit flips. So they also depend their position and the amount of bit flips that you're causing. It depends on the hardware configuration and on other low-level properties of the machine that you're running on. But also another property is that everything is reproducible. So once you found some bit flips on one machine, you can reuse the same machine again to trigger those bit flips. So this is what we're going to work with. In terms of defenses, by the way, I skipped already the software defenses for Rowhammer. Maybe we can talk afterwards. But let's look at the hardware defenses. What do we have here? We have target row refresh, which basically it's a hardware mechanism that will track the amount of accesses to these rows. So if you access these rows many times in a short period of time, and you are above a certain threshold, then what will happen, this mechanism will refresh the adjacent rows, so the rows that I just showed now. This is something that is fairly new. It's been pushed in the LPDDR4 standard, but however, it requires collaboration with the firmware. So the BIOS has to somehow enable this, and also the memory controller has to be aware of all of these things. So by default, it doesn't come enabled, for sure. Now, this is one of them, which probably we will see in the future how it evolves. But since Rowhammer was discovered on servers, everybody thought that ECC is kind of good enough. So error correcting codes are another defense for this. However, error correcting codes weren't really designed to defend against Rowhammer. They were designed to defend against bit flips or memory errors, but those bit flips could be completely different. So they do have some different things. But however, ECC is still a good defense probably. But the question, and also everybody knew that once you have enough bit flips, actually you would bypass ECC. Okay, but the question is, how good is this error correction code for Rowhammer? By the way, error correction codes are really used a lot in servers. So Rowhammer wasn't really so much of a problem for, let's say, cloud providers, because they have good hardware with ECC support. So our research, we want to target now to understand. We want to target and to try to answer this question: how can we how good is ECC, and in the end, how can we bypass ECC? Or is it possible? Or how many bit flips it will take at the end? Let's start with a gentle introduction in error correction codes, ECC 101. There will be ECC 102. I hope we can make it till there. So out of all the bit flips that we have, some of them will be detected by the error correction code, and some of them are not detectable. Some of the detectable ones will be actually corrected. This is the role of the error correction and detection at the end, right? For Rowhammer, in the Rowhammer context, the interesting bits are the ones that are undetectable, so the silent corruptions. So if we can cause these the bit flips in this, let's say, data set, then we can have a Rowhammer exploit. We want to do this without triggering the detectable ones. So if we corrupt a bit and that one is detected as being corrupted by the error correction code, if the machine or if our target machine is configured correctly, it should probably crash the machine. So we want to avoid always the detectable ones, and our goal would be to find undetectable bit flips. But the thing is that the boundary between undetectable and detectable, it's not really a clear boundary. So what do I mean by that? For instance, let's take sec_dead. I'm going to use this term not in a very thorough way, but let's stick with this. So sec_dead stands for single error correction and double error detection. So the thing is that for sure any one error will be corrected. And for sure, 2 errors will be detected, but there's no specification, and there's no specification about what will happen with more than 3 bits. So there's no guarantee there. So what actually happens in practice, depending on the implementation, some of the 3 bits errors will still be detected, but not all of them. There will be 3-bit errors which aren't detected. So actually we want to look for these 3-bit errors, let's say, that are not detected. So as you can see, the boundary again between undetectable and detectable, it's not really that smooth. So we want to provoke, to cause the silent memory corruption. Yeah, so to further target our presentation, it will be something that we want to find the minimum number of bit flips and also their position that ECC cannot detect. So why the minimum number? Well, because with Rowhammer we cannot actually trigger an infinite number of bit flips, right? So with Rowhammer we can trigger several bit flips, and we want to have the highest chance to actually trigger bit flips such that the ECC cannot detect. So this will be our goal for this reverse engineering and the motivation behind it. So I think I hope I convinced you why error correcting codes are interesting in the Rowhammer context. Let's see why reverse engineering of error correcting codes, right? Because I already gave you the theory, so it should be kind of clear. Well, as I said, the boundary between undetectable and detectable is not really clear. What we can, it's not really clear. So why reverse engineering then? Let's see how ECC is implemented and what ECC I'm going to target in this presentation. So first of all, let's see how it works. So the CPU wants to write some data to memory. What it does, it will compute some extra control bits with the data that that the CPU wants to write, and it will write both the data and both the control bits at the same time. When the CPU wants to retrieve data from memory, it will retrieve as well the control bits and as well the data. And then it will do some sort of computation on this data and figure it out if there was an error. If there was an error, it may as well correct it. So everything is implemented, the ECC that we target is implemented in the CPU. There are some interesting properties with this implementation of ECC. So as I said, it's implemented on CPU die, so it's a purely hardware implementation. There's no much, there's no code behind it. Probably there is some very low code. It is completely transparent from the CPU in the sense that you cannot explicitly access the ECC part, the control bits, and other properties are that optionally for reliability and high availability in servers, you would want to figure it out when errors are actually corrected. For example, if you have lots of errors within a certain DIM, maybe it's time to replace that DIM. So this is a good practice. And also it must be very fast because this is on the critical path and the data is not too useful if it has uncorrectable errors on it. So you want to detect this and you want to act and you want to implement it very fast. But another interesting property, and probably that's why we're doing reverse engineering, is that this is largely undocumented. Maybe you can find in some CPUs what kind of guarantees they will offer you, like a SecDead kind of implementation, but this is about it. You wouldn't find all the details. Sometimes you can find some details about errors, but most of the times you just say you just find that it will correct it will detect 2 errors and not much more than that. So and as I said, the implementation, the boundary between detectable and undetectable, the one that we want to look for, it's kind of implementation specific. So how can we read this the ECC bits? Well, there are several ways. For any problem you have, there's a tool probably. You can always buy a tool, which is a testing equipment used to test to test memory behavior and to actually get certification. You can use these kind of tools to debug, but to debug your memory controller. But this is a fairly expensive tool, and we don't want to do that. And in addition, there are other tools, but sometimes they do not support the reading the ECC part. And these tools are fairly expensive. The question is, can we do better than this? Well, with reverse engineering, I'm going to show you two things. We can. I'm going to show you 2 attacks that are aimed to reverse engineer the ECC, the control bits, right? One is based on a fault injection, and one is based on a cold boot attack. So this is the kind of the long introduction for my presentation. Let's see. This is the ECC 102. I hope you don't get scared. Anyways, I cannot see too well from here. So we have this parity matrix, which is let's say, it's a parity matrix which is just a matrix which is used to encode and decode the data that the CPU writes and reads. So this is the construction that has nice properties and that is easy to implement in hardware. Most of the times things are implemented with a XOR operation. The takeaway from this one is that everything is based on matrix multiplication. When you're encoding data, so when the CPU writes data to memory, you just multiply the data that you want to write. You multiply it by this parity matrix. And when you're reading the data, you compute a so-called syndrome by reading the data and again multiplying this data with the parity matrix. So again, the encoding and decoding, they do have in common the parity matrix. And in short, the parity matrix will give you the ECC code. Now we can view this parity matrix a bit different than all of these operations. So basically, if you have one bit asserted in the data that you want to write, basically you're going to select just one row of the parity matrix. Vice versa, if you have one error in the data that you just retrieved, you're going to select a row from the same parity matrix. So in other words, basically this the syndrome, so the error that you are going to observe, the syndrome and the ECC part are really tied together through this parity matrix. Okay, so the question is, how do we reconstruct the ECC? So I'm going to try to rephrase the previous slide because I think there was way too many things on it. So stated differently, for sure, the syndromes, so the intermediate results of ECC, are reported to the operating system. Now, this syndrome is as well used to do error correction and detection, and we have some equations there. You can also view the ECC as a big table, which is indexed by a symbol, which is a bunch of bits that are adjacent, and a symbol on one direction, and the other direction could be the symbol value. Also, when you're computing the syndrome, another simplification that you can do is just to read to do a XOR between the ECC that you retrieve from the memory and the ECC that you just computed yourself. Intuitively, we could say that ECC decomposes bit by bit. As I said, everything is implemented in XOR, and this is a property of the way the ECC was chosen to be easy to implement in hardware. So there are two interesting properties. The ECC value decomposes bit by bit, and the ECC is very related with the syndrome. So basically, the ECC, we could say, is equal with the syndrome. So if we treat ECC as a function, and let's assume this function takes a 64-bit value input, and this input has just only one bit asserted on one of the positions. If we write this data, a ECC value will be written in the control bits. And then when we read the data, if we fault the exact bit that we asserted previously, then we will observe the syndrome. And that syndrome actually is exactly the same as the ECC that we just wrote to memory. So this is the base of our attack. So the last equation is kind of the most important one from this old math thingy. Okay, so that was the base of our attack. Now I'm going to introduce the fault injection based reverse engineering. So the thing is that, to rephrase everything, if you have a single bit error in every position, then this will allow us to actually recover all the complete ECC function, and with this we can predict what value will be written in memory. So what we have to do to run our attack is just to cause a single bit flip in the data that we're reading, and then try to observe this syndrome. And with the syndrome, we can compose the whole ECC table. But how can it cause these single bit errors? Again, we can look through documentation, and some motherboards, they do have, some memory controllers, they do have resources such that you can actually do memory error injection, but this is not really something that is standard. Another way is to actually use Rowhammer to inject these errors and then observe the syndrome, but then it will be a bit hard to see where the error was injected, and also you don't have that much control. So these are, and also the bit flips will be corrected if you do just one. So that is hard to observe, and again, for any problem, you'll have a tool. The problem with these tools is that they are fairly expensive, and I'm not really sure if it comes with the NDA or not. But in any case, if you see a tool like that without a direct price, it means that it will take time to actually get to that tool. So what can we do better than this? Well, so we will propose a cheap and effective fault injection method, and I really think it's very cheap. But we should start now to see where the bits are actually stored. So this is a non-ECC DIMM, and yeah, obviously the bits are stored in the black chips. But the takeaway is that this interface is fairly standard. Actually, this is a DIMM, right? So for example, the ECC DIMM has only one extra chip, and those are the control bits. While we don't exactly care about the control bits, it's actually good to know how things are mapped in reality. Again, all of this interface is standard. So for instance, let's say we want to fault a single bit, right? We can start with the data sheet of that DIMM. DQ maps to one of the bits. Probably DQ0 maps to, let's say, the least significant bit. This is pin number 3. Okay. We also have, it's easy to get the pin number. So again, this is a standard interface, and also you can find some of these numbers on the PCB itself. So we know where pin 1 is. We can locate easily, even on the motherboard, where DQ0 stands, where the signal that we want to fault is. Now, how do we actually fault a signal? Well, we just want to create, so it's an electrical signal. We just want to create a perturbation, right? We should be able to inject some sort of current or play with, we should be able to just do some sort of perturbation there. Our first idea and the way we started this project was a bit random. So we had like a pre-test, I would say, where we just use a piece of wire of, I don't know, 5 centimeters and with a thickness of 1 millimeter, and we just stick it there in that hole where the arrow of DQ0 points to, and we use a lighter. Yeah, so this was a piezoelectric lighter, and this piezoelectric lighter actually had like a big EM spike, so a big electromagnetic spike that was picked up by our antenna, which was just a simple wire. So we could see ECC errors at that moment, and we said, yeah, maybe we should do a project now because this looks like fun. But yeah, then I realized, yeah, but I don't want to move that wire. Maybe, I don't know, maybe the lighter will break. So let's see if we can build something even better than this. Wow, so there's a nice signal there. Next to DQ0, we have a, let's say, a ground signal. Maybe we can short that with this thing. So we built a very expensive probe with from two syringe needles that are, yeah, they are apart, like so. The distance between the two tips of the needle is exactly the distance between two holes in that DIMM socket that we just saw before. And also this is isolated, so I mean it's plastic in between. Yeah, so this was our probe. This worked fairly well, so we also used like a tweezer to short out the two needles, and we are observing errors. It was a bit more stable than the previous solution. It worked nicely, but then we realized that actually the VSS is next to most of the signals, right? So we can do the same for any signal. This was great, and actually if you look at the footprint of a DIMM socket, you could see that next to any data signal, you would find a VSS signal. So the idea is that we have this mechanical constant probe that we can just move around and short the VSS with the data signal. Yeah, so pretty good. So in this way, we managed to do fault injection in all of the positions of DQ. And by the way, this footprint also holds true for DDR4. So we started with DDR3, but this is true for most of the DIMMs out, I mean, for all of the DIMMs out there, because usually you want to put a VSS signal next to a data signal, such on the PCB. And the reason for this is you want to keep signal integrity as much as possible. So this is something that, again, is a standard thing. So yeah, our probe, and we will have a fault injection demo with our demo gods in MP4 format. Yeah, with no sound. Yeah, so that's my hand, and I just set the probe there on DQ3, on DQ0, and VSS. So currently there's no fault being injected because the two needles are they are not in contact. The machine is running, so there's no problem there, so fairly stable. That's yeah, modified memtest version that just reads from memory, random memory, and you can see on the right hand there are the syndromes being reported. Yeah, this used to have sound, but I stopped. And right now I'm using the tweezer to short out those two pins, so you can see the errors on the right. They're going up. Okay, so this was our needle. So it was a nice way to actually inject errors. And also this method would work as well on. I guess I can. Yeah. So this method works on any machine in theory, as long as you can observe the syndrome. So let's recap a bit this attack to see what it actually takes, because I just showed you how to inject an error. So the idea is that the CPU will fill the memory with all bits asserted, because this shunt acts as a pull to 0 now. Then the CPU will start to read, so we can write a nice program to just read from the memory in infinite loop. We can short a specific signal, and with our custom probe, and then we observe the syndrome, and we gather this. We gather it in a nice file, and then we just move the probe to another signal, and so on until we recover the syndrome for every position of this let's say 64 bits. Then we use the equations that I was showing you before to solve and to figure out the ECC table. So all the syndromes, if we observe all the syndromes for all the bits being faulted, then we can recover the full ECC function. So in short, this is the way the attack works. Is there an undesired behavior? Well, we didn't get any machine crash. That was fine. I guess I was paying attention to stuff. And the thing is that ECC will correct just one bit error, so that's why you won't get a machine crash. And yeah, as I said, we can even boot Linux and write a nice user space program that does the same stuff like memory accessing. Yeah, we also figured out that the memory bus is quite resilient, because if you think about it, when you design an expensive server board, you want to have some sort of protection of, I don't know, random DIMMs being sticked in your board, right? We got no magic blue smoke, but yeah, your mileage might vary. I'm not saying you should do this. Yeah, there are some downsides as well. So indeed, it doesn't look safe for the victim. However, we didn't have any problem. It's a bit error prone. So those yeah, pins are fairly small. They are next to each other. You have to somehow coordinate when you're moving the probe with I don't know, with someone else writing down a number for you or things like that. It's also time consuming. We can also make a joke how many grad students it takes to inject enough errors. And luckily, to answer this question, probably it doesn't matter, because yeah, because we have no life, I guess. Yeah, so this is a comment that was posted. So our work was, and as well with the ECC Rowhammer, our work was already, yeah, we published in the news, and yeah, someone commented that we have no life. But anyways, if we have no life, then I guess we know how to get around this. We will get a life, and what we do, we're going to build another way to attack this ECC memory. To actually figure it out, again, the ECC function. So there were other drawbacks of our approach. As I said, it's fiddly, and you have to do it for every target that you want to figure it out. What if you can do it just for only one target, and then use this information to actually build a nice memory dumper based on ECC? Okay, so this is the target of the second part of our talk. So a gentle introduction in cold boot attack. So we know that memory content survives after power off. Of course, it's like a limited period for which it survives, and this highly depends on temperature. We can access this uncleared memory either on the same host, which is called probably a reset attack, or on a different host. So basically what we can do is we have like a victim machine. And we have a host machine, and we have some interesting data in the victim machine, which ends up in RAM. We cut the power of the victim machine. We just quickly take the DIMM out and put it on the other machine, and then we start reading the memory there, and hopefully we will get some plain text keys or passwords. So this is the cold boot attack in short. Right now, if you're lazy and you cannot do it like very quickly, you should use like a spray like that, which is for fault location. And that spray will cool down your DIMM such that you don't lose that much information. So actually, the retention time, we could recover like, I don't know, more than 95% of the data that the victim just wrote by just having the DIMM around 1 or 2 degrees Celsius. So it's not really crazy. You don't have to go to the North Pole for this. Yeah, so we also have a demo with this one, and the demo god is with us again. So I'm going to explain the cold boot attack. So there are 2 machines here. So yeah, the one on the up is the victim machine, for which we don't know the ECC, and the one down is the host machine, for which we know the ECC. So the idea is to figure it out, the ECC on the unknown one. We have some freezing spray. I actually have several boxes now. Yeah, it's non-conductive. So yeah, the goal is that we want to recover the ECC function of the victim machine. Wow. So we're going to start with the host machine being powered off. And the victim machine, of course, writes some data to memory. I'm going to apply the spray. So I'm not stressing myself that much. So it's like 2 or 3 times, it's more than enough. Yeah, data is being written right now to memory by the victim machine. Yeah, I had to set up a timer to cut the power to the server. I apply more spray, and 10 seconds should be about now. Okay, I'm moving the DIMM, and I'm turning on this machine. Right, so right now the host is booting, and yeah, we wrote a program such that we, again, log all these syndromes that we observe. Right. So this also dumps all the information on the serial because that machine is not too stable, though. And right now, we recover all the syndromes. So the idea is that we know the data that we just wrote. We know the data that we just observed. We know as well the ECC function of the host machine. And yeah, everything, again, is based on XOR operations, and we can recover the ECC right now on the victim machine. So this is a recap. So at the end, we just gather the syndromes on the host, and we can learn the ECC victim by applying those equations. So this was the cold boot attack. However, there's a problem. So when a machine with a ECC memory boots up, it has to train the memory, and as well any other machine that boots up from scratch has to somehow train the memory link. But if it's ECC memory, it's very important to clear the memory before you use it. Why is that? Because the memory initially has, let's say, random data, so you cannot make an assumption there. And this random data is as well valid for all the chips, including the control bits. So then you cannot start reading the memory without getting ECC errors. So what any machine with ECC will do, with ECC memory, will first try to clear out the memory or try to write something to this memory. This is a bit bad for our attack, right? Because right now we're going to, when we're moving the DIMM from the victim to the host will first reset this memory. So how come we got syndromes before? Well, what are our options? So we look through BIOS if there's a memory clear enable or disable switch, but there wasn't any. I know some other boards, they do have one, but we were using this one. So yeah, what can we do? Well, the obligatory IDA Pro screenshot. This is the BIOS. It's not a UEFI BIOS. It's a kind of old version BIOS, the canonical, the old one. And we managed to reverse engineer parts of the BIOS and especially find this awesome call. And yeah, the call, we just knocked it out, which yeah seemed reasonable. the machine was still stable. This goes in the direction of Alex's introduction, the keynote speaker from yesterday. So yeah, you have to look around when you're doing reverse engineering, and we observed that some similar code was contributed to core boot by AMD, and this code was including as well the memory initialization part. So that was kind of cool. There was some checksumming bypass happening at some point, but yeah, I won't go into details. I had to reprogram several times the BIOS chip. Not really that complicated. Maybe, it took some time, I would say, at least at that. Right, so with this hack in mind, so we managed to do the cold boot and to do the generic victim, the generic memory dumper, right? So this memory dumper right now works for any machine that has ECC memory, right? So you just can use any victim right now with this machine. And I'm going to open source parts of this one, so you can actually use the same board if you want and flash your own BIOS image. I guess you can flash it now, even through some nicer interface than the clip that I have there. Right. So I talked about the fault injection attack. And how do we reverse engineer with that, and also with the cold boot, right? But yeah, it remains the question, okay, so how about the Rowhammer part? Well, this talk is not really about this the attack itself, but the idea works like that. So we propose the ECCploit attack, and it goes like this. First, you have to find the ECC algorithm of the machine that you target. And this is fairly easy to do. So if you have access to some cloud machine, you can always do cat proc CPU info and look for the CPU that is being used there. After that, you can try to get a similar machine that you control. And the ECC function is not really is not different at all between the two. So if it's the same version of the CPU, it will be the same ECC function. Then the next step would be to do some sort of online analysis and try to find correctable bit flips on the target machine. You want to do this without going detected. So this kind of will take some time. The idea is to find one correctable bit flip at a time. Now, once you have enough correctable bit flips, you can, and once you know the ECC algorithm, you can combine all of these correctable bit flips to cause a silent memory corruption. So this was our goal from the beginning. And basically, in this way, with the ECC algorithm, basically you know the clear boundary between undetectable and detectable bit flips. The Rowhammer exploit is fairly similar with the known one. The only differences are in the phases, in the initial phases when you have to gather all the bit flips. So this would be the main difference, I would say. Right, but again, on this talk, I was focusing only on reverse engineering, the ECC functions. You can find more on our paper at SMP this May. So in short, the Rowhammer exploit will work even in the presence of ECC nowadays. It is kind of slow. That's least to say. You can find more information there. Now, I don't have a logo, but I have a quilt for you. So this is based. The quilt was generated based on some ECC properties of that we recovered. So basically, I'm not sure if you can see, but the main diagonal of this one is completely black. So there are like black dots there. Every pixel on the So this is like 128 by 128 pixel image, and every pixel represents the Hamming distance between a ECC value that was obtained by just asserting that position in the data stream. So that's why you'll have the same ECC on the main diagonal. Yeah. To wrap it up, I showed you two attacks: the fault injection and the cold boot attack, with the goal in mind to reverse engineer the ECC functions. And these are important because in this way we can understand how much ECC buys us for the Rowhammer attack and how good of a defense that is. I hope this picture makes more sense now for you. Thanks.
So we got about 15 minutes of questions, 4 questions. Do I see any hands? I call it the after lunch effect.
So, Lucian, so I was wondering, you said you, oh, do you hear me? Yeah. I was wondering, you said you can recover the ECC for any kind of machine now with the dumper.
Yep.
Does it make any assumptions on like how many bits this ECC can correct or like what kind of ECC it is?
No, yeah, I would say there's no much of a difference. The key point is that you have to disable the errors. So this dumper will access lots of errors which are not correctable. So you have to make sure that this dumper is good enough to stay alive, even if lots of errors are not corrected. And once you have this one which is fairly stable, it doesn't matter. It's just a matter maybe of remapping or reusing the equations somehow differently. No, but yeah, indeed, the host that we choose has 128 bits per, let's say, ECC word, and we use this one to reverse engineer a machine that has 64 bits per ECC word. This was a difference that we actually observed it while reading the data. So we had to cope with it somehow in the sense of doing the proper equation and proper computation. But this is easy to spot. So yeah, it requires some work if there's a complete mismatch between them, but you can still get around.
Okay, thanks.
Yeah, thank you for the talk. Maybe a dumb question, but what next?
What next? Yeah, good question. So, in terms of Rowhammer attack, or?
No, it's really interesting to understand what's the next steps. I mean, maybe you have some ideas about it.
Yeah, let's see. So we can go in the direction of more reverse engineering if we want to. So for instance, there is memory scrambling happening, and this can be as well reverse engineered with the memory dumper that we have. So you can read the scrambler if you want in this way. Other things is to actually understand the mechanism of again, memory scrambler in the context of Rowhammer. Is it important or not? So this would be maybe interesting to figure it out as well. But so far, it seems not to be a good, yeah, it doesn't matter, actually. Yeah, what next? So, yeah, I don't know.
Okay, thank you.
We can definitely talk more about this, and we can brainstorm about it.
Yeah, I was curious, why are some of the bit flips undetectable? And when you were looking at that, did it seem like there might be a scenario where you could not actually successfully exploit it due to the undetectable range?
Due to what, sorry?
Like you rely on only correctable bit flips, right? Like you have to be within that area to successfully exploit it?
So the correctable bit flips, to actually figure them out, is the online analysis, and then you carefully look for these bit flips, and you can actually make sure that you're going to get at most one at a time, and that one is always correctable. So this is part of the Rowhammer exploit. And once you got one in one row, and then you can, let's say, get one in the same row, but not at the same time, then you know right now that you have 2 bit flips. Maybe you can find another one, and you'll have like 3 bit flips. And right now, both you detected them online, right? So, but you detected in a way that they were just corrected. And the question is, how do you detect them being corrected, right? Once you detect them being corrected and you have like 3, you can say, okay, according to my ECC function, which I reverse engineer offline, I can trigger again the same 3 bit flips, but this time all 3 at a time. And I'm going to generate ECC that is actually not detected at all as being an error. So in this way, we managed to combine the corrected ones, the whole 3 ones, in an uncorrectable one.
Perfect.
Uncorrectable 3 ones. Of course, right now we have to change. So if we look at the Rowhammer a bit down, if a PTE entry will map over this one, then these 3 bit flips must be asserted. So if you have the same direction, then it becomes a bit of a dependence, Rowhammer dependent on the data now. But yeah, we simulated this one, and we can probably get around this one as well.
Thank you.
Okay, then let's have another round of applause.
Thank you.